Welcome to some special antiderivatives. So note, we still have not seen how to integrate natural log, the natural log of x, or inverse trig functions. It turns out that integration by parts can be used. So let's start off with integrating natural log. So to find the integral of the natural log of x dx, we're going to use integration by parts. We can't put, oh, I need to update my screen, I apologize. We can't use natural log as dv since we do not yet know the integral. So we will take natural log of x as our u and just 1 or dx as our dv. If we then differentiate natural log, we wind up with 1 over x. And if we integrate 1, we get x. Now I'm going to stop here because 1 over x gets more complicated as we integrate. We could, however, also just rearrange that bottom row or resplit the product. But let's go ahead and just stop here. We have a positive product on the diagonal, and we will subtract the integral of the bottom row. So we are looking at the integral of the natural log of x. One moment. Right, sorry about that. We have the integral of natural log of x dx is equal to the natural log of x times x minus the integral of 1 over x times x dx. This is simply x natural log of x minus the integral of dx, and we wind up with x times the natural log of x minus x and then plus c. You will often also see this integral written in the format, the integral of the natural log of x dx is equal to x times the natural log of x minus 1 in parentheses, right, factoring out the x, and then plus c. So again, integration by parts allowed us to find an integral of natural log that we otherwise did not know. Next, let's go ahead and take a look at integrating inverse tangent. So if we want to find the integral of tan inverse of x dx, we can pull the exact same trick. So we'll go ahead and set our u to be tan inverse of x, set our dv to just be 1 or dx. Differentiating down the left, integrating on the right. Taking the derivative of tan inverse of x, we get 1 over x squared plus 1. Integrating 1, we wind up with x. Take the positive product of the diagonal and then subtract off the integral of the bottom row product. We wind up getting that the integral of tan inverse of x dx is equal to tan inverse of x times x minus the integral of 1 over x squared plus 1 times x dx. That integral on the right lends itself perfectly to u substitution. If we set u equal to x squared plus 1, then we have du is 2x dx. And so that means that the x dx that we can see is just 1/2 du. So our integral that we are working with, we have the first component of x times tan inverse of x. Then we are subtracting off the integral of 1 over u times 1/2 du. At this point, we have x times tan inverse of x minus 1/2 times the natural log of the absolute value of u and plus c. Plugging back in our u of x squared plus 1, we have that this integral is equal to x times tan inverse of x minus 1/2 times natural log of x squared plus 1, then plus c. So the integral of tan inverse of x dx is x times tan inverse of x minus 1/2 the natural log of x squared plus 1 plus c. So as you can see, integration by parts allows us to integrate things that otherwise we would not have known how to integrate. It won't allow us to integrate all such functions, but it certainly can be helpful.